Hi, welcome to the first video on my proof by induction integration series. So let's begin with how we're going to attempt all proof by induction integrations. So base case and assumption like normal, always going to be the same. This is pretty much going to be the same for every method that we ever look at. Next, what we're going to do is we're going to consider n equals k plus 1. But remember, our goal of induction is to involve the assumption. So we've just assumed it's true for n equals k. We then need to involve this assumption, because otherwise, what was the point of making it? So to do this for integration, the trick is using parts. So we're going to use parts to involve our assumption. Once we involve the assumption, it generally just boils down to either like a limit problem or just basic algebra manipulation. So let's have a look at an example. So I've said that In is equal to integral from 0 to infinity of xn times e to the minus x dx for n being greater or equal to 0. Prove that In equals n factorial, where n is an integer. So this is a very famous function actually. This is called gamma of n. This is the continuous factorial. You may have seen it before. Now we want to prove that it matches the factorial for all integers. That's the whole point of this video. So let's have a look. So first of all, let's look at the base case. So base case, n equals 0, with the integral from 0 to infinity of x to 0 e to the minus x dx. This is equal to the integral from 0 to infinity of e to the minus x dx. Well, this is equal to minus e to the minus x between 0 and infinity, which is equal to the limit as x goes to infinity of minus e to the minus x minus e to the minus 0. So we're subtracting the 0, but it's already a negative, so it's going to be plus. This is just the same as 0 plus 1. And well, on the other side, we have 0 factorial, which is in fact equal to 1. We're not going to go into the reasons for this. I'm sure you can find lots of videos online for why 0 factorial is 1. So yeah, true for base case. So it takes a little bit longer than just a regular base case to what we're used to, but still not too bad. Next, we're going to assume that it's true for n equals k, i.e. the integral from 0 to infinity of x to the k e to the minus x dx is equal to k factorial. We're then going to consider n equals k plus 1. So we've got the integral from 0 to infinity of x to k plus 1 e to the minus x dx. So now we need to try and use parts to involve our assumption. So what I'm going to do is I'm going to select a u and a dv. My goal is I want to keep this the same, but I want this to be x to the k. So to do that, I need to differentiate this. But if I integrate this, does it stay the same? Well, it does. Kind of. It becomes minus e to the minus x. But that's fine because we can always just take constants out to the front. So we don't mind introducing a constant. Well, we're actually going to introduce a constant here. But that's fine. So we have u equals x to the k plus 1. dv equals e to the minus x. That means du is going to be k plus 1 x to the k. And v is going to be minus e to the minus x. Now, we do diagonal is already integrated, so we have x to the k plus 1, e to the minus x, and we have a negative between 0 and infinity, minus, and then we do vertical is being integrated. So integral from 0 to infinity of k plus 1, x to the k, e to the minus x, and we're going to bring the negative out to the front, so this becomes a plus now, dx. Okay, so first of all, let's have a look at this part here. So this is going to just be a limit. So at the limit as x goes to infinity of minus x to the k plus 1 e to minus x. Well, exponentials beat polynomials, so this is going to be 0. Minus the limit as x goes to 0 of minus x to the k plus 1 e to minus x. Well, again, this doesn't go to 0, whereas this goes to 0. So this here is going to be 0. This here is going to be 0. Plus, well, I'm going to bring out the constant to the front. So this is k plus 1 times the integral from 0 to infinity of x to the k e to the minus x dx. Well, we saw from our assumption this is k factorial. So there's k plus 1, k factorial, which is k plus 1 factorial. We've seen this trick with factorials many, many times. Check my inequality series, you'll see that we use it, I think, 2 or 3 times actually. But yeah, so we get to what we want. So as true for n equals k plus 1, when true for n equals k, and true for base case, n equals 0 by, and again I'm going to abbreviate it, by mathematical induction, it must be true for all n bigger or equal to 0, where n is an integer. But again, we're not going to state it. There's not really much point. We've kind of assumed it at the top here. But yeah, I hope this was helpful. In the next video on proof by induction integration, we're going to have a look at a harder example. This one's quite interesting because, well, we get a continuous factorial. What's more cool than that?